All right, so can there be a function increasing to the left of any x equals c and decreasing to the right of x equals c and not have a relative maximum at x equals c? Well, basically the definition of the first derivative test tells us that as long as it's increasing up until that point c and then it's decreasing right after, this has to be a relative maximum on that number line here. So no matter what, it's always going to be a relative maximum. The only time where it gets a little bit tricky is if I were to have a function that would look something like this on C, because I could have it go increasing up to there, but this would still be a relative maximum in a place where that would occur. So this is just a nice little review of what we have going on here. And so I really like the use of the number line because at this point I've got my critical point C, and in this scenario it's negative and then positive, which we drew like this before. And so that means that at C I've got that relative minimum. The same is true for all the other ones. It's just nice to see it in a graphical form rather than just having it written down. So when this is plus and plus, like we had before, this just keeps going up. So it doesn't ever reach a relative max or min at that point. So be careful when locating these relative max and min using the first derivative test. So the first derivative test is based on dividing an interval into subintervals. So those subintervals are based on these critical numbers. And remember, those critical numbers are anything that made the first derivative equal to 0. So remember, a critical number is at x equals c such that f must be defined at x equals c. So f of c must exist, and there must be a point on the graph where y equals f of x at x equals c. However, f prime of x may change signs on opposite sides of the discontinuities of the graph of f. So just be careful of that. It might change and be different wherever that is.